Hey everyone, today we will be discussing covalent bonding and covalent molecules. What are covalent bonds? These are bonds that share electrons between them and have electrostatic attractions between a pair of electrons and the positively charged nuclei. Covalent bonds are made up of two or more nonmetals. Here below you can see the positively charged nuclei attract to the negative pair of electrons. Some covalent bond properties include low melting and boiling points, high volatility, varying conductivity, can form molecular or network solids. Some exceptions to these properties include diamond, graphite, and sulfur dioxide. Covalent dot diagrams can be drawn with a very few simple steps. First, you add up the total number of valence electrons in the given elements of your molecule. Then, you draw the structure, where the first element of the molecule goes in the center of the model, except for hydrogen. Then you draw on the bonds and the surrounding atoms of the central atom, and then you add in extra electrons to complete the octets, and if there's not enough electrons, you put in double or triple bonds. Check if the electrons in your diagram matches the calculations from step 1, and some exceptions to this octet rule include hydrogen, helium, lithium, beryllium, and boron, because these elements are too small to have 8 valence electrons. We're going to practice drawing some diagrams, so feel free to do it on your own and pause the video, but I'm going to do it step by step. So, I know that carbon has 4 valence electrons and 3 hydrogen atoms, which have 1 valence electron each, gives me a total of 3 more electrons, and I know that chlorine has 7 valence electrons, which brings me to a total of 14 electrons to work with. So I place my carbon in the middle, and then my surrounding atoms of hydrogen and chlorine. After that, I draw in my bonds, and then I use my remaining electrons to fill in octets. And now my diagram is done. Because I've used up all my electrons, all of my elements have stable octets, and yeah. So for CO2, I know that carbon has 4 valence electrons, and 2 oxygens give me a total of 12 electrons, which brings me to 16 electrons to work with. I know that I put carbon in the middle, and then I put oxygen and oxygen around it. I draw in my bonds, and then fill in my octets. Now, I know that carbon doesn't have a complete octet, so I'm going to erase 2 pairs from the oxygens to create 2 double bonds, which should bring me to a complete dot diagram with 16 electrons here, 16 electrons up here, and all my elements have stable octets. Now, some quick bond facts. Bond length is the distance between 2 bonded nuclei. Bond strength is the energy required to break the bond. Bond length normally increases as the atomic radii of your elements inside the molecule increases. Bond strength increases as you add more bonds, so a triple bond has more strength than a single bond. However, as your bond strength increases, it pulls your 2 atoms closer together, which actually decreases the bond length. Over here, you have 2 hydrocarbons, one with a single bond and one with a double bond. My hydrocarbon with a single bonded carbon is going to have a larger bond length than my double bonded carbon, because my double bonded carbon will pull the 2 carbons closer together. Some molecules to remember is that CO2 and O2 both have double bonds, and N2 will always have a triple bond. Molecular geometry. This explains that electrons will repel each other and causes bond angles. Electron domains are all the electron locations, which include lone pairs and bond sites. CO2 has 2 double bonds, which means it has 2 bonding sites and 2 domains. Ammonia has 3 bonding sites and 1 lone pair, giving me 4 domains. My linear shape will have either 1 domain with 1 bond or 2 domains with 2 bonds, giving me 180 degrees either way. like in these three molecules. My trigonal planar shape will have three domains with three bonds and 120 degrees for the bond angles, like in BH3. My tetrahedral shape will have four domains with four bond sites with about 109.5 degree bond angles, like in CH4. My pyramidal shape will have four domains with one lone pair and three bond sites with about 107.5 degree bond angles, like in ammonia. My bench shape will have four domains with two bond sites and two lone pairs with about 104.5 degree bond angles, found in water. My bond polarity is determined by the difference in electronegativities of elements. The greater the difference is, the more polar a bond is. If I have zero difference, then this creates a nonpolar bond. Ionic bonds are very polar because they have a great difference in electronegativities. So for example, I have a H2O molecule here. My oxygen and hydrogen both have a great difference in electronegativities, which creates a very polar bond. However, in my Cl2 molecule, they both have the same electronegativities, creating a difference of 0 and a nonpolar bond. My molecule polarity is determined by the symmetry of the molecule. Nonpolar covalent molecules have a symmetrical shape, while polar covalent molecules have an asymmetrical shape. You can use SNAP, or symmetrical, nonpolar, asymmetrical, polar, to understand this better. This also has something to do with the even versus uneven distribution of charge. So I know that silicon tetrachloride has an even distribution of charge since it has a symmetrical molecule, and that all of my surrounding elements of the central atom have equal amounts of electrons, and them being all chlorine. However, with HCl, I have two different elements, and chlorine has 6 more electrons than hydrogen, which creates an uneven distribution of charge and an asymmetrical polar covalent molecule. Now, here is some practice you can do doing the drawing dot structures and identifying bond and molecular polarity. I'm going to wait a few seconds, so feel free to pause the video while you complete the practice. So here you have carbon tetrafluoride, which has a polar bond and a non-polar molecule since it has a symmetrical shape, and the electronegativity difference between carbon and fluoride is great. Hydrogen sulfide, you have a polar bond with a polar molecule because of its asymmetrical shape and the electronegativity difference between hydrogen and sulfur. In the nonpolar bond in pH3, this is due because P and H both have similar electronegativities, creating a nonpolar bond, but it creates a polar molecule due to its asymmetrical shape. IFAs are the attractive force that hold molecules together in solid or liquid form. Polar molecules have dipole-dipole and hydrogen bonding and LDF IFAs. LDF. These are the weakest IFAs. This is what holds nonpolar molecules together, like in CH4. Dipole-dipole. These are what holds polar molecules together, and the positive side of one polar molecule is attracted to the negative side of another polar molecule, like how the positive side of hydrogen is slightly attracted to the negative side of chlorine in HCl. Hydrogen bonding is a bond between H and either F, O, or N, or fluorine, oxygen, or nitrogen. Hydrogen is on the phone is an easy way to remember this. And keep in mind this is an attractive force, not a bonding type. Now these are the IFAs listed according to strength, metallic being the strongest, LDF being the weakest, and it's important to know that as IFA strength increases, so does melting and boiling point. Quick recap of the video: covalent bonds, properties and dot diagrams, bond strength, length and polarity, molecule geometry and polarity, covalent IFAs. Hope this video helped. Thank you and bye.